In this video, we're going to take a look at section 3.5 on rational functions and their graphs. The first kind of problem we have in this section is finding the domain of rational functions, and this is a task that we have done previously in chapter 1. The setting's a little bit different, but the idea is still the same. So let's go ahead and take a look at what a rational function is, right? So a rational function is a function that is our quotients. How do I want to say this? Okay, I should just read what's on the screen. Rational functions are quotients of polynomial functions. So the root word there in rational is ratio, and that indicates that it's going to be a fraction. And so that's what we see here. We have the quotient of polynomial functions. That quotient means we're dividing, which means we have fractions. What is nice about this restriction for this definition is that we are dealing with polynomials in the numerator and polynomials in the denominator, right? So p of x here is a polynomial function, so it can't have negative exponents, it can't have exponents that are fractions. And q of x in the denominator is also a polynomial. So this is going to make our rational functions somewhat well behaved because we are requiring that these are polynomials, so we won't have to worry about square roots or other crazy kinds of math that might show up there, absolute value, whatever else you can think of. The domain for a rational function is the set of all real numbers except the x values that make the denominator equal 0. So we're going to start with the assumption that the domain is all real numbers, and then we're going to selectively remove any numbers that would make me divide by 0, which is, again, something that we have done previously in chapter 1 with the rational equations that we looked at back then. So let's take a look at this example down here. We have f of x equals x plus 8 over x squared minus 64. So f of x equals x plus 8 over x squared minus 64. I just want to rewrite it because it's kind of blurry over there. I apologize for that. When it's a fraction, the print can get kind of small. All that matters here for the domain is the denominator. That's all we're worried about. When is that denominator going to equal 0? Those numbers that would make the denominator equal 0 need to be removed from the domain, and then everything else can stay. Right, so what I want to do is consider this situation where x squared minus 64 is equal to 0. Right? That's what I'm interested in finding out because those are the things that I don't want. Right? So what's not allowed to happen is x squared minus 64 equaling 0. By solving that equation, it's going to tell me the values of x that I'm not allowed to use, so those need to be removed from the domain. So this is a quadratic equation. You know, on the homework, you might have some that are a little bit easier than what you see here, and you might have some that are a little more challenging. This one's not too bad. You actually don't have to factor it. You could just solve it for x by adding the 64 to the other side and taking the square root. I like factoring. So let's go ahead and factor this. X plus 8 times x minus 8. We set each factor equal to 0. And we get two solutions here. Right, we're going to get x equals negative 8 and x equals positive 8. So let me scroll up there so hopefully you can see that. It's not too far in the corner of your screen. And remember, what we're finding here are the values of x that are not allowed, right? Everything that's happening here is not allowed to happen in the actual equation. So x is not allowed to equal negative 8, and x is not allowed to equal positive 8. But x can equal anything else. Now, if you pick a different number, any number really, in this equation, you're probably going to get pretty terrible answers because the equation's a fraction. So we're not talking about how nice the answers are going to turn out. We're just talking about whether you can get an answer or not, right? So if you plug in negative 8 for x, you don't even get an answer, right? It makes you divide by 0 and the whole thing's just busted. If you plug in positive 8, same thing, you just don't even get an answer. Anything else you plug in, you'll get an answer from. So anything else can be, it's workable, right? We can use it even if we don't like the answers we're getting. So the way I like to visualize this is on our real number line, right? So I always like to show 0, but what we want to skip over is -8 and +8. So I'm going to put little open circles above those numbers, and then I'm going to shade everything else in, everything to the left, everything to the right, and all the numbers in between, right? And that's my domain. To write that as an interval, we have to describe each separate region. So this region over here is from -infinity to -8. This region here is from -8 to +8, excuse me. And this region here is from 8 to infinity. And then we join those regions together with union symbols. So this would be the domain for that function. Now, if you're observing, you might have noticed that x squared minus 64, based on the way it factors, this fraction actually reduces, right? We have an x plus 8 on the bottom, we have an x plus 8 on top. Those cancel each other out. This actually reduces to 1 over x minus 8, which is relevant for graphing that function, but is not relevant for the domain. You have to find the domain of the function you're given, not the function that it could become, right? So it doesn't matter that after you reduce, -8 is okay, right? Only +8 makes you divide by 0. That doesn't matter. In the original function, both -8 and +8, the way the function was presented would make you divide by 0, so that's what we want to go with. All right. Okay, so that is the domain. You'll have a few homework problems on that. What we're ultimately trying to accomplish in 3.5 is graphing these rational functions. And because of the issue of dividing by 0, these functions, the graphs, get chopped up into separate pieces. And so this is what we're looking at here on the screen. One direction in which the graph gets chopped up is a vertical direction, so we can chop the graph up into pieces by making vertical cuts, if you will. And those vertical cuts occur because of the issue of dividing by 0 in the function. So for example, the problem that we just did, oh, I guess that one, because it reduces, it actually behaves a little bit differently. But because we can't plug +8 into that function, then if you, and this is x equals 8, right? So if you find 8 on the x-axis, the graph cannot exist here. This is where x is equal to 8, and since that's not allowed in the function, it's also not allowed on the graph. So you cannot have any points on the graph that touch this vertical line or cross through that vertical line, because that number is off limits in the equation, it's off limits in the graph. And because that line is infinite, right, it goes down forever, it goes up forever, that's chopping our graph into two separate pieces. And what's going to happen is on one side of that vertical line, the graph it'll kind of act like a polynomial graph, there'll be some curve to it. But as it gets closer to that vertical line, it'll keep getting closer and closer, but it will always maintain some distance away from it. So it's going to look something like what you see on these charts over here. It might do something like this, where it'll keep getting closer and closer, but it will never cross or touch that vertical line. It could also possibly go like this, right? These are kind of our two choices here, right? So I'm not sure, we'd have to plot points to figure out what's going on there, but it's going to do one of those two things. The point is, as it gets closer to this vertical line, the graph will approach it and get closer and closer and closer, but it never touches it and never crosses it. This concept of a line that the graph approaches without crossing or touching is called an asymptote, right? So it's kind of this funny word here. And this particular type of asymptote is a vertical asymptote, because it's a vertical line that the graph approaches without crossing or touching. And then, so that vertical line cuts the graph into two separate pieces. So one piece will be on the left, and then you'll have a piece of the graph that's on the right. And again, same thing. It could do something like this, or it could do something like this, right? It just kind of depends on some other details, which we're going to talk about as we go through the rest of this lesson. And so we'll have part of the graph on the left-hand side, the other part on the right-hand side, and they're just chopped into two separate pieces. And those two pieces will approach that vertical line without crossing or touching from both sides. All right, so this is what we're looking at here in this graphic, right? The description that you're seeing at the bottom of these graphs is a pretty technical way of describing what's happening with the asymptote. And this is a primer for the way you talk about things in calculus. So I think I've mentioned this before in class that one purpose of this course is to prepare students who are on that path to take trigonometry and calculus. So we want to give them some exposure to the language that you're going to be using when you take calculus. I'm not sure if on the homework they're going to make you talk about it in this way. So, but just to kind of break it down for you, because it's not too complicated. What's happening here is that this is saying as x approaches a. Now a is the vertical line here, right? This is where x is equal to a on that vertical line. This is saying as the graph approaches that value of a, but there is a plus sign next to the a, which means from the positive side, from the right-hand side, essentially. So as x is approaching the graph from the right-hand side, which is what we're seeing here, right? The graph is approaching that vertical line from the right-hand side. It's heading up, right? It's going up the asymptote, not down the asymptote. And so remember, f of x is our y variable. So what we're saying here is that y goes to infinity. So as x approaches a, as the graph approaches that vertical line, is what that means, from the right-hand side because of the plus sign, y is going to go up forever, right? Positive infinity is up, negative infinity is down. Right? Sorry, it's a really bad infinity symbol, would be down, right? So if it had headed down, this would be y approaches negative infinity, right? So that's how you interpret that notation. This one, as x approaches a from the left-hand side, right? Because there's a negative sign there. So as the graph is approaching that vertical line from the left, y is going, the graph is going up, right? The y values are increasing, the graph is heading up, which is what we see happening here, right? So as the graph approaches that vertical line, it's heading up. That's how you interpret that. Here, as x approaches a from the right-hand side, so as the graph approaches that vertical line from the right, this time the y values are getting smaller because the graph is heading down. So negative infinity means the graph is heading down. Positive infinity means it's heading up. Right, so that's how you interpret that. And I'm only giving you that explanation just in case that's the way it's presented on the homework. Where do we get the vertical asymptotes? As I mentioned, it's the numbers that would make you divide by 0. Those become your vertical asymptotes. Right? So that's where those arise from in these problems here. And I think that's what these examples are about. So locating the vertical asymptotes. Let me zoom in here a little bit. If f of x is equal to p of x over q of x, if that is a rational function in which p of x and q of x have no common factors. Now what this means is that you can't reduce. So if you've already reduced that fraction and it can't be reduced any further, and a is a 0 of q of x, this means that a makes you divide by 0. So if that number a makes you divide by 0, then x equals a is a vertical asymptote of the graph. It's the same numbers that you're finding when you're determining the domain. The same numbers that you're worried about making you divide by 0, those become your vertical asymptotes. All right. So for example, we have g of x here, x plus 3 over x times x minus 3. So for the vertical asymptotes, again, the numerator doesn't really matter, again, unless you can reduce it, and that's something that's going to happen in h of x here in just a minute. This doesn't reduce, right? None of the factors are the same, so I can't cancel anything out, even though they're close, right? X plus 3 and x minus 3 are close to each other, but they're not exactly the same, so they don't cancel out. So to find the vertical asymptotes, it's going to look exactly the same as the first example that we did. We take the denominator, we set it equal to 0, and then we solve for x. It's already factored, so we don't have to really do much work here. We just set each factor equal to 0. We get x is equal to 0, and x minus 3 is equal to 0, which gives me x equals 3. Now again, these are the values of x that are off limits to that equation. This is what's not allowed, right? X is not allowed to equal 0, and x is not allowed to equal 3 in this function, which is what makes them the vertical asymptotes. These are the vertical lines that the graph cannot cross or touch because those numbers are off limits in the equation. So I'm not going to put a line through the equal sign like this because we're saying these are the asymptotes. But in the equation over here, x is not allowed to equal 0, right? That's why I have that as a vertical asymptote. So that is the answer here, right? So the vertical asymptotes for g of x are x equals 0 and x equals 3. So this graph gets chopped up twice, right? Here's where x is equal to 0. Right here on the y-axis. Here's where x is equal to 3. And so the graph gets chopped up into 3 pieces, right? You'll have part of the graph will exist over here on the left-hand side, part on the right-hand side, and there will be a piece of the graph in the middle. And they're all like separated from each other because of those asymptotes. All right. This one is a little different, and this, you'll notice in the directions, I didn't really read it to you, but the directions say, find the vertical asymptotes, if any, and the values of x corresponding to holes. So what we're going to do, so g of x doesn't have any holes, right? We just have the vertical asymptotes, and that's it. There's no holes, right? So if it asks you about that, for this one, you would say there are none. There are no holes in this case. For h of x, we actually do have a hole in the graph. So let me explain kind of how that works. So let me write this out so you guys can read it. I'm sorry, it's small print on the screen. So really, we're just going to approach this problem in the same way we did the last one. And in the same way we did the domain, right? We're going to take the denominator and we're going to set it equal to 0. So that, again, to boil it down for you, to make it as simple as possible for this, how do you find the vertical asymptotes? You take the denominator, you set it equal to 0, and you solve for x. That's how you get your vertical asymptotes. Okay. We're going to solve this by factoring, right? So, because again, I like factoring. That's the way I like to solve these, even though we could solve it directly for x if we wanted to. This factors as x plus 5, x minus 5. We set each factor equal to 0. All right, and we get -5 and +5 as our two results, right? So this is going to give me x equals -5. This will give me x equals +5. And again, these are my vertical asymptotes. Let me pick a different color here, right, vertical. These are, I guess maybe I should say, these are the candidates for being vertical asymptotes here. Right. Now it's possible that one of these could become a hole instead of a vertical asymptote, and that will happen if the fraction can be reduced, which this one can, right? So if I go back to the original function, and I replace the denominator with its factored form, right? It factors as x plus 5, x minus 5, just like we saw over here. We notice that we actually have an x minus 5 in the numerator as well. So this x minus 5 cancels out with this one. And we end up with 1 over x plus 5. So that's what it reduces to. So the factor that gets left behind, that still gives you a vertical asymptote. So that expression is what will give us our vertical asymptote, which is -5, right? -5 is what would make that equal 0, so that's still the number that's off limits. That one's still going to give me a vertical asymptote. The other one that we found over here, the +5, pick a different color here, the +5 that isn't showing up over here, that one's going to be a hole. Because it's still off limits, it just won't be a line that the graph approaches without crossing or touching. It will just be a point that gets plucked out of the graph. So the graph will kind of, have a smooth curve to it up until -5, and then a smooth curve after that. But then at the point where x is equal to +5, you'll have an open circle. Because in the original, because again, what matters is the original function, that number is still off limits. Even though it gets canceled out when we reduce, in the function as it was given to me, 5 is still not okay to use, so that point has to get removed from the graph. It just doesn't become an asymptote. It just becomes an open circle. So the graph might look something like this, again, without going into the details of graphing it. You still have the vertical asymptote at -5. So you'll have, let's say, the graph might do something like this. It might go like this in this direction, and then it might go like this in this direction here, right? What's going to happen is at +5, we are going to have to erase that point off of that graph, right? And so we'll have an open circle here at that point, and that, I guess I kind of filled it back in again by accident, but there we go. So that point just gets removed from the graph. So it'll still be a smooth curve. It'll just have this hole in the middle of that line because that number is off limits in the original function. So I'm sorry, I know it's a complicated extra detail. Usually when I teach this topic, I avoid talking about that extra thing because it's already complicated enough with all the other stuff going on, but it's in this textbook, so we need to talk about it. Okay, now, unfortunately, there are other types of asymptotes. So there's the vertical asymptotes, which you find by taking the denominator and setting it equal to 0. And then, again, check to make sure it's actually a vertical asymptote, not just a hole in the graph. But there are two other types of asymptotes that I really like to think of as a single type. So there's only ever going to be one of these other types. So for vertical asymptotes, you can have more than one. Like we saw here, we had two. Sorry, I didn't switch to the pen. We had two vertical asymptotes here, which would chop the graph up into 3 different pieces. You can have 3 vertical asymptotes. That would chop the graph up into 4 different pieces, right? So this is what we're talking about over here. So there's really no limit to how many vertical asymptotes might occur. In general, you're only going to have 1 or 2. I doubt you're going to have a problem with 3 because it really starts to get pretty complicated after that. So 3 would be the worst, I think, that you would have to deal with, but hopefully most of them just have 1 or 2. But for the horizontal type or the third type, which we haven't talked about yet, there's only one of those, and it will either be horizontal or that third type. It won't be both. So you have one or the other. And so this is kind of what it looks like as you're seeing in the graphic here. A horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of a function f. If f of x approaches b, right, that's the number being referenced here, as x increases or decreases without bounds. I know that's pretty complicated. Again, that's somewhat the language of calculus, but just look at the visuals, right? It's the same as a vertical asymptote, except it's a horizontal line, right? And so as the graph goes to the right, it's going to approach, the y values approach this number b here, and they will get closer and closer to b without crossing or touching, usually. And that's what makes it an asymptote. Here, as the graph goes to the right, the graph is also approaching b, except from above. So really, you could use plus signs and minus signs if you wanted to on that. You would say, in this case, f of x is approaching b from above. Here, it's approaching b from below, but it doesn't seem to be worried about that. All right. Same thing's happening here. Now, here's the case where you have an exception, where the graph does cross the horizontal asymptote once, but then it approaches without crossing or touching afterwards. So you have to always, there's just, for me, whenever I'm graphing these, I always have this fear in the back of my mind, like, what if it's one of these exceptions and I just didn't find the points to help me determine that? Because there is a chance that it does sometimes cross the horizontal ones. There is never a chance it will cross the vertical ones. Those cannot be crossed under any circumstances. But the horizontal ones, there are exceptions like that. But eventually it does approach without crossing or touching. All right, so this is what horizontal asymptotes look like. We'll have those in conjunction with the vertical asymptotes. All right, so locating a horizontal asymptote. Okay, so here are the 3 different possibilities, and they are based on the degree of the polynomials in the numerator and the denominator. So notice that here, the degree of the numerator is n in this graphic here, and the degree of the denominator is m. I'll try to enunciate that so it sounds different. Right? So the degree on top is n, the degree on top is m. If the degree on top, which is n, is less than the degree on bottom, right? So how do I want to say this? If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is just automatically at y equals 0. There's no calculation to do, it's just automatically that's the horizontal asymptote for that graph. And again, there's only one, there won't be another one. Right? If the degrees are the same, right, if they're equal to each other, then the horizontal asymptote is at y equals a sub n over b sub m, which sounds like a complicated formula or whatever, but it's really not. It's just a ratio of the leading coefficients. That's all that is, right? So we take a ratio of the leading coefficients from the polynomials in the numerator and the denominator. And that becomes the horizontal asymptote. That's only if the degrees are equal. And then the last case, which I kind of marked up on here, if the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote because it will be the third type. It'll be what's called, I think, oblique. That's at least what we called it in the old textbook. Could be diagonal, whatever. It's a diagonal line instead of a horizontal line. All right. So let's take a look at these examples here. Again, I'll write these problems out so you can see them in case they're really small on your screen. We have 15x over 3x squared plus 1. It wants me to find just the horizontal asymptote, which is good because in this case, there is no vertical asymptote because it would be imaginary, so which is kind of a weird case that we probably won't see very often. Find the horizontal asymptote if there is one of this graph. Right? So to determine the horizontal asymptote, we want to look at the degree of the polynomial on top and the degree of the polynomial in the denominator. The degree of the polynomial in the numerator is 1, right? Because the highest power of x is x to the first power. The degree is 1. The degree for the denominator is 2, right? Because that's the highest power of x there. And since the degree of the numerator, I don't know why I use a different color there. Let's just kind of do this. Since the degree on top is smaller than the degree on the bottom, the asymptote is just y equals 0. The horizontal asymptote is y equals 0. All right. Okay, so and it doesn't matter what the degrees actually are, it's whether the top one is smaller than the bottom one. If the top one is smaller than the bottom one, it's just y equals 0. Let's take a look at the next example. Again, I'll write this out so it's a little bit more legible. We have g of x equals 15x squared over 3x squared plus 1. The degree of the numerator is 2. The degree of the denominator is also 2. And so they are equal in this case. So if they're equal, then the horizontal asymptote will be y equals the ratio of the leading coefficients. So the leading coefficient for the numerator is 15, and the leading coefficient for the denominator is 3. So I will take 15 over 3. That will be my horizontal asymptote, which of course we want to divide or reduce as possible. So this reduces to 5, right? So it's going to be y equals 5. All right. Now, for the last one, you can probably guess there's a very predictable pattern here to these problems. They basically follow the order of that graphic, right? So the first example was number 1 in that graphic. The degree of the numerator was smaller, so the asymptote's y equals 0. The second example was number 2 in the graphic. The degrees were the same. And so we took a ratio of the leading coefficients. So this is going to be number 3 in the graphic, right? The degree of the numerator is going to be larger than the degree of the denominator, right? The degree here is 3 for the numerator. The degree for the denominator is 2. So the degree, how do I want to say this? Maybe let's do it this way. What color do I want to use here? Oh, geez, okay, I've used them all so far. The degree of the numerator is bigger, which means there is no horizontal asymptote. I'm just going to abbreviate asymptote because I don't want to write the whole thing out. Okay, so that is how horizontal asymptotes work. You just have to kind of memorize these rules about the degrees of the polynomials in the numerator and the denominator, and those lead you to your answers. That's, again, there's math behind it, right? What we're doing here is a big shortcut that we're trying to do without going into the actual math behind it. If you're interested in like the math that justifies these results, I'd be happy to share that with you maybe outside of class sometime. It's based on calculus, right? So again, we're just really, a lot of the topics we're doing at this point are just kind of verging on the edge of what you would learn in calculus. We're getting as close as we can without actually doing calculus, right? So it's kind of like a calculus chicken a little bit, right? It's like, how close can we get it without actually doing calculus? So that's kind of where we're at right now. We're getting as close as we can to the topic without actually going into it. But if you're interested in it, I can give you like a brief overview of like how these horizontal asymptotes come about based on the degrees and all that stuff, all right? Okay, so, looks like we're not going to talk about the third type, or maybe that comes later. Okay, yeah, and they call it slant asymptote. So the other textbook called it oblique. I guess there's just different names for it. So before we get into that third type of asymptote, where a thing, just gets even messier, we want to talk about how do we graph these rational functions, because that is the point of everything that we're doing. The asymptotes play a very important role in the shape of the graph. So if we want to graph these rational functions, we have to know where the asymptotes are located, and then we have to plot some points, and then we draw the graph connecting the points and approaching the asymptotes without crossing or touching. So that is our basic goal that we're having here. So let's kind of see the order in which they talk about it. Now again, first they want us to determine if the graph has any symmetry. I really don't like that step of any of these graphing problems because it's kind of a lot of work, and a lot of times it just doesn't pay off. Like, you find that there's no symmetry anyways. But again, they're asking you to determine, is there symmetry to the y-axis, which means it's an even function, or is there symmetry to the origin, in which case it was an odd function. This time we don't really have a shortcut for that. We can't do like what we did in 3.2. You can't just say, well, if all the exponents are even, it's an even function. Actually, I think that is true. But there's other ways it could be even as well. So you have to use the basic definitions we talked about back in chapter 2. I kind of hope the homework doesn't ask about it, because otherwise I'd say let's just kind of skip that step. If the homework's going to make us do it, okay, then we probably should talk about it. Then it says find the y-intercept, which is exactly the same as what we did previously back in 3.1 and 3.2. You plug in 0 for x, and then you solve for y, right? You find f of 0, basically. That's your y-intercept. If there is one. Now, in every graph we've done so far, there's always been one y-intercept. This is the first case where maybe there might not be one. Depends where the asymptotes are located, right? Then they want us to find the x-intercepts, which again, we do in exactly the same way. We set y equal to 0, and then we solve for x. Except that this time, because again, this is like y right here, right? When we set that equal to 0, we're getting a fraction equal to 0. So again, the equation becomes more complicated. Then it suggests that we find the vertical asymptotes, like how we did earlier in the video. And then the horizontal asymptote, notice how that is singular. There is only one. And then this one's saying if there is one, so maybe there's a case where there isn't one. I'm trying to think, is there? Oh, because it could be the other type. It could be the slant asymptote. Right, so find the horizontal asymptote if there is one. If there isn't a horizontal one, it would be a slant one. There's always going to be one of these kinds of asymptotes. If it's not horizontal, it'll be the more complicated type, which we're going to talk about in just a minute. Plot at least one point in between and outside of the asymptotes and the x-intercepts, right? because the x-intercept is going to give you 1 point, or maybe 2 points, depending on how many there are, which will help us graph. But in any area where there's no points, you need to plot at least 1 point so you kind of know what the graph's going to do, right? We don't need a lot of points here to graph these because the asymptote's going to do a lot of the work for us. All we kind of need is 1 point in an area, and then from that 1 point, we approach the asymptotes without crossing or touching. The asymptotes kind of direct us. All right, use the information obtained previously to graph the function between and beyond the vertical asymptotes. Okay, so let's give that a try here, right? So follow the 7 steps above to graph the rational function. So I'll just put this all the way up to the top here. I'll write this out a little bigger so I can make sure you guys can see this when you're watching the video. All right, so we have this rational function here. So first it wants us to determine if there's any symmetry. Again, I really would like to skip this step, but just in case it's on the homework. The way you test to see if it's an even or an odd function is you replace the x in the original function with negative x. So I'll have 4 times negative x squared over negative x squared minus 9. And then you simplify with that negative sign in there. Now, whenever you square a negative, it just comes back out positive. So negative x squared comes back out as just x squared. Same thing happens here. This just comes back out as positive x squared. And we end up getting the original function back. So in that case, right, so these are equal, right? In that case, the function is an even function. If you replace x with negative x, and then you simplify and you just get the original function back, you have an even function. If you get the negative of the original function back, that's when it's an odd function. Right. This time we got the original function back out, and so that tells me it's an even function, which means this graph is symmetric to the y-axis. So let me spell symmetry correctly. So symmetric to the y-axis. All right. So we'll just keep that in mind when we go to draw our graph, that we want to make sure the graph to the left of the y-axis matches, is the mirror image of the graph to the right of the y-axis. All right. So that's step 1, determine if there's any symmetry. This time we did have a symmetry. Step 2, we want to find the y-intercept. That's what it listed for us next. So step 2, we're going to find the y-intercept, if there is one, and in this case there is, and we're going to find that by plugging in 0 for x. So we'll get 4 times 0 squared over 0 squared minus 9. That's going to give me 0 divided by negative 9, which is going to give me 0. So the y-intercept is at 0, 0. And so I can plot that point, right? So we have a point here. 0, 0, and that's all you get out of that. The y-intercept gives you a point. And again, there's nothing else you can really do with that information except graph the point. The third thing they suggested we do is to find the x-intercepts, if they exist. So again, there might not be any. Depends on the asymptotes, depends on the details of the equation. To find the x-intercept, we are going to replace y with 0. So remember, f of x is our y variable. We're going to plug in 0 for y, and so we're going to get 0 equals 4x squared over x squared minus 9. And this looks like a pretty scary equation, but it's not as bad as it seems. The only way a fraction can equal 0 is if the numerator is equal to 0. So in fact, we can actually just ignore the denominator. When you're finding the x-intercepts, you can ignore the denominator. So the shortcut for the x-intercept is just to set the numerator equal to 0. Set the numerator equal to 0, and then solve for x. You can drop the denominator. So we're just going to have 0 equals 4x squared, right? Without the denominator being there. Which I kind of like, because to find the vertical asymptotes, you set the denominator equal to 0 and solve for x. I kind of like we're using each piece of the equation to get some information out of it. Now, solving this for x is kind of annoying for what we're going to get out of it. You're going to divide 0, or sorry, not divide 0. You're going to divide 4 on both sides, but you get 0 out of that, right? The 4's cancel out here. 0 divided by 4 is still 0. And then we're going to take the square root of both sides to get x by itself, but the square root of 0 is still 0. And so we end up just getting the same thing we already knew about. We get the x-intercept is 0, 0, but that's a point that we already had, right? That's the y-intercept. So we end up just reconfirming a point that we already graphed. Okay, but sometimes you'll get a different point, or even 2 points out of the x-intercept. And even though it's the same point that we already discovered with the y-intercept, on MyMathLab you'll have to type in an answer for both of these. So you kind of need to know 0, 0 is both the y-intercept and the x-intercept in this case. Step 4 is to determine the vertical asymptotes. And we do that by setting the denominator equal to 0. So let me I'm going to zoom out a little bit here so we can kind of see the whole problem. Wow, it's way up there actually. Okay, a lot further up than I thought it was. And let me switch colors here so this will stand out a little bit. We're going to take, I got to zoom out a little bit more. Right there, okay. We're going to take the denominator and set that equal to 0. So we're going to have x squared minus 9 equals 0. That's how you find your vertical asymptotes. And in this case, we're going to have 2. Okay. So I'll solve this by factoring, because again, that's the way I like to solve these. I know I've said that a bunch of times on this video, right? And then we set each factor equal to 0. You get x plus 3 equals 0. X minus 3 equals 0. And then we solve for x in each case, and so we get x equals negative 3 and x equals positive 3. All right, and those are my vertical asymptotes. So there's 2 of them in this case. So we can graph those vertical asymptotes as vertical lines passing through those numbers on the x-axis. So I need a vertical line passing through 3 on the x-axis and a vertical line passing through negative 3. Right? So I'm going to draw vertical lines here. I guess I'll do these in red because, again, the graph cannot cross these vertical lines. And we're going to do them as dashed lines, right? Because they're not really part of the graph. They're sort of invisible barriers. Right? But those 2 invisible barriers will chop my graph up into 3 parts. Right? I'll have a part on the left-hand side, I'll have a part in the middle, and I'll have a part on the right-hand side. All right. Okay. That's step 4. Step 5 is to look for the horizontal asymptotes, or I should say asymptote. There can only be one of these. Go ahead and just write that out here. Horizontal asymptote. Again, this is based on the degree of that function, the degree of the numerator and the degree of the denominator, I should say, right? So in this case, the numerator, the degree is equal to 2, right? And for the denominator, the degree is also equal to 2, right? The highest power of x for both of them is 2. So the degrees are equal, which means my horizontal asymptote is y equals the ratio of the leading coefficients. The leading coefficient on top is a 4, the leading coefficient of the denominator is a 1, and so I will take a ratio of those leading coefficients. So 4 divided by 1, which gives me 4. So it's y equals that ratio. So my horizontal asymptote is at y equals 4. So we're going to find that on here as well. So this would be where 4 is located right here. And I guess I'll keep with the same color. So it's going to be right here. Now again, sometimes the graph can cross that boundary once, but afterwards it will approach the asymptote without crossing or touching. Sometimes in the middle, it's like the asymptote's not there. So in this case, I'm kind of wondering if this horizontal line is an asymptote on the outsides, but in the middle, it's like it doesn't count. That happens sometimes. So we'll have to find out by plotting points. So we found all the asymptotes, we found all the intercepts, and we really don't have a whole lot to go on here. So for example, on the left-hand side, there's really 2 possibilities here. Either the graph is above the horizontal asymptote, in which case it's going to look like this, where it will approach the asymptotes in that manner, or it could be below the horizontal asymptote, in which case the graph's going to look like this. That's basically our two options. There is the off chance that maybe this has the exception and maybe it crosses and then comes down like this. That's another thing that could happen here. But if that's going to happen, it would happen very dramatically. So I think we would notice it if we plot a couple of points. So that's what we need to do next. So for me to know whether the graph is up here or down here, I have to plot points to figure that out. And I'm really just curious, is it above 4 or is it below 4 on the y-axis? So I'm trying to find a nice empty space to work in here. So let's look at, this will be step 6. We need to kind of make a chart of values. And I want to figure out what the graph is doing over here, which means I want to pick x values in this region. And the best one for me to pick, the smallest one, is -4, right? So I'm going to pick -4 for x. I'm going to have to plug -4. I don't want to, but I have to. I have to plug it into that function there. So we're going to have f of -4 equals 4 times -4 squared over -4 squared minus 9. Right, so we're plugging that number into that function, and I'm just going to zoom out a little bit more so we can have some room to work here. And let me kind of put a different color here. So this is not related to the horizontal asymptote, that's this area here. So when you multiply this out, you might want to use a calculator. The numerator is going to give you 64. It's going to be 16 times 4, which is 64. The denominator is going to be 16 minus 9, which is going to be 7, which again is not a great number to have. And I need to know basically, is that above 4 or is that below 4? So we might want to convert that to a decimal, right? So 64 divided by 7 gives me 9.1, right? So this is equal to about 9.1, right? And so that's where I want to graph this, which is definitely above 4. So that point is going to be somewhere like, so at -4 on the x-axis, the y-coordinate's like 9.1. It's going to be just above 9, which is right here, right? Now, I would think if this was going to cross that horizontal asymptote, excuse me, I think I need to take a drink of water. I don't know. I don't think it'd be that high up at that point, but maybe I'm wrong about that. So maybe it'd be worth looking at what you get when you plug in -5 as well, just to get another point to see, is it gradually approaching the asymptote or is it heading like straight down towards the asymptote? Because if it's going straight down, it might cross the horizontal asymptote and then approach it from underneath. But I'm guessing that's not what happens here. So just real quick, if I plugged in -5, what would I get here? I would get on top, that'd be 25 times 4, that'd be 100 on top. And then 25 minus 9 would be 16 on the bottom. 100 divided by 16 is going to be 6.25, which is still, again, it's a pretty gradual drop, right? So at -5, it would be like, I don't know, about right there or something. So that seems to me like it's kind of going in for the landing, if you will. So I think it's just going to look like this. So that's what the graph will look like. So the asymptotes are guiding me. So from those points, I approach the asymptotes without crossing or touching. And the asymptotes guide what the graph looks like. Let's hop over to the right-hand side and do the same thing there. Again, +4 would probably be our best choice there. I'm going to go back to this mess I made over here, but this time I'm going to plug in +4. But because I guess we can kind of cheat here. We do know it's symmetric to the y-axis, so it's going to be the same answer, right? And we can see that over here, right? 4 squared is 16. 16 times 4 gives me 64 again. 4 squared is 16. 16 minus 9 gives me 7. We get the same answer. We get 9.1 again, right? And in fact, the graph's going to have to behave the same way over here. And so, let me pick a different, I don't know what color to pick here. So +4 will be at 9.1, which is right there. And then from there, the graph is going to approach the asymptotes without crossing or touching on that side as well. And it should mirror what's happening on the left-hand side because of that symmetry. Now in the middle, we need to plot some points as well because, again, that one point, I'm kind of nervous because here's the things that could happen in the middle. It could just do like this. It could be like sort of like a parabola, sort of. where it just kind of heads, it can't really head up. It's not supposed to anyways, because it would run into the asymptote, right? So my guess is it probably does this, but it is possible. I've seen graphs that do this, where it'll kind of snake through like that and just ignores the asymptote in the middle, which can happen for horizontal asymptotes. Or it might even be like this. So we really need to plot a couple of points there as well. So continuing with our plotting of points, I already have 0, so I don't need to plot that point again, but I'll pick 1, right? 1 seems like an easy one to work with. I'll do that down here. So I'm going to plug in positive 1 for x. I get 4 times 1 squared over 1 squared minus 9. I don't know why I keep writing minus like that. And that's going to give me 4 over negative 8, which is going to give me negative 1/2. Right? So I'll get negative 1/2 here, which means it goes below, right? So let me pick a different color. So for 1, it's going to be negative 1/2, which is going to be about right there. Again, we can also use the symmetry for negative 1, since that's on the other side of the y-axis. I have to get the same value for y there, so it's going to look like this. So I guess my other options can't work because of the symmetry, right? So it has to kind of look like this. So it's going to have sort of a parabola shape to it, so it's going to look like that. So plot points in between and outside of all the vertical asymptotes, and then with those few points, approach the asymptotes without crossing or touching. And that gives you your graph, which again is a very sophisticated graph. But with the asymptotes and plotting a few points, we can figure out what that graph looks like. All right, and I'm sorry, just standing back and looking at everything we just did, I can imagine how you guys are feeling right now. So I'm sorry if it feels really overwhelming. And I wish if I was more organized in how I wrote things out, maybe that would help. I'm just not very organized, unfortunately. So this is how my brain works. This is what things look like in my head, unfortunately. So, all right, we got one more topic, I think, which is on the slant asymptotes. And I'm sorry the video is going on kind of long. So let's go ahead and talk about this last topic here, and then we'll be done. I'll try and make this as quick as I can. Okay, so identify the slant asymptote. The graph of a rational function has a slant asymptote if the degree of the numerator is more than the degree of the denominator. So this is the case where there's no horizontal asymptote. If the degree on top is bigger, it becomes what's called a slant asymptote. And to find that, unfortunately, there's no shortcut. You can't just say y equals 0 or y equals the ratio of the leading coefficients. What you have to do is divide the denominator into the numerator, and whatever quotient you get from that division, that will become your slant asymptote. It'll be y equals whatever that quotient is. Right? So here, the degree on top is 2. The degree of the denominator is 1. And so the degree on top is bigger, which tells me there is no horizontal asymptote. Right, so if it asked me about horizontal, I'd say, well, there's no horizontal asymptote here. But there is going to be a slant asymptote instead. Let's get letters here. So there will be a slant asymptote. I guess I should put that here as well. There's no horizontal asymptote because instead we have a slant asymptote. And the only way to find that slant asymptote is to take the denominator and divide it into the numerator. So that's what we have to do here. And this is long division. So this is something we talked about back in 3.3, where we did an example of this back then. So we ask ourselves, what do I multiply to x to match that first term, which is x squared? I have to multiply by another x. X times x gives me x squared. So this one's kind of weird. You subtract to see what's left over. The highest power cancels out. There is no x here to bring down or to combine together, so we just have the -4 left, which means I'm done dividing because x cannot go into -4, which means this is my quotient and this is my remainder, right? The -4 is going to be my remainder, which for the asymptotes we don't care about. We cared a lot about the remainder for the p's and q's stuff. We don't care about the remainder here. What we care about is the quotient, right? So the quotient is right here. And so y equals that quotient is going to be my slant asymptote. Okay, now to graph this, we are going to graph the slant asymptote. So let me maybe write that over here too. This is my slant asymptote. Why am I doing that? I'm putting the y first for some reason. Okay, slant asymptote right here. And this is going to be, what step was it? Step 4, I think. So 2 is the y-intercept, 3, no, it's step 5, right? The horizontal asymptote. Well, in this case, it's not horizontal, it's the slant asymptote. That's where you would find that. And you would graph it, and again, it's a linear equation. So you're graphing a line, right? The y-intercept is 0, and the slope is 1. So what you're going to do is start at 0, and then the slope of 1 means you go up 1 to the right 1. So up 1 to the right 1 gives me that point there. And then I would just connect those points with a line, but I want it to be a diagonal line, right? So it's going to look like this. Sorry, not a diagonal line. It's a diagonal line, but what I meant to say was a dotted line, which I kind of did a bad job of that too. So it should look something like this. Okay. All right, so that's my slant asymptote, which again, the graph will approach without crossing or touching. But we still need to find all the other details to graph this. I'm going to skip the symmetry part of this. So I will just kind of leave this to you to figure out. Just looking at it, I can tell that this will actually be an odd function. So when you test for that symmetry, by replacing x with negative x, you should find you get the negative of the original function, which makes it an odd function, which means it's symmetric to the origin. So there actually is a symmetry here in this example. All right. Step 2, we want to find the y-intercept. So we plug in 0 for x. I think I'm just going to zoom out here a little bit. And so we will have f of 0 equals 0 squared minus 4 divided by 0. The problem there is we get negative 4 divided by 0, which is undefined, which means there is no y-intercept in this case. So that's what happens when there is no y-intercept. It's because you're dividing by 0. So the graph will not cross the y-axis because of that. Which means we're going to have an asymptote there, right? Which we haven't got to yet, but we will see that here in just a minute. The x-intercept, or intercepts, there could be more than one. We get that by setting y equal to 0. So we get this, right? So we set y equal to 0, so 0 equals that fraction. Remember, the shortcut here is that the only way a fraction can equal 0 is for the numerator to equal 0. So I can just ignore the denominator. I set the numerator equal to 0, and I solve for x. And we actually do get some answers here, right? This factors is x plus 2, x minus 2. I'm trying to say I'm already kind of over time. I was trying to keep this to 50 minutes. I'm already at 57. So I'm just going to jump to the punchline here. And we get 2 x-intercepts. These are not my vertical asymptotes, right? So be careful, because if you just put x equals this number, it could be a vertical asymptote if you're not careful about thinking about how you got that number, right? This is an x-intercept, right? Which is why I like writing these as ordered pairs, right? This is negative 2, 0, and positive 2, 0. It is not the vertical asymptotes, right? These are points, not lines. Right, so we can plot these points on our graph. So let's zoom out again a little bit here and maybe scroll down. Right, and these are going to be on the x-axis. So we have positive 2 and we have negative 2. Right, so we have this point here and this point here. I'm sorry, I put the negative 2 off to the side, but that looks kind of confusing, doesn't it? So I'll put it up here. Whoops. We'll try to put it up here. Okay, so negative 2. All right, so we have those 2 points. We do have a vertical asymptote, so let's maybe jump back up this way to the original function. And so here, the vertical asymptote, this is step 4. Again, there could be more than one, like we had in the last example, but this one will only have one. You take the denominator, which is x, you set it equal to 0, you solve for x, but it's already solved for x. It's x equals 0. So that's my vertical asymptote, which is the y-axis, right? So that is my vertical asymptote. Sorry, I tried to do dotted lines, but it doesn't quite cooperate with me on that. Okay, and then we get to, and we already did step 5, we already have the slant asymptote. Step 6 is, okay, plot points in between and outside of all the vertical asymptotes, but we already actually have enough points, right? The x-intercepts give me enough points for me to actually draw this graph, so I don't have to find any more points, actually. So we can kind of skip step 6 here because we already have enough information. So from this point here, I know the graph will approach the asymptotes without crossing or touching, right? So I'm just, as it goes to the right, it's going to kind of hang along the slant asymptote, getting closer and closer without crossing or touching. And as it heads to the right, it's just going to go straight up the vertical asymptote without crossing or touching. On the other side of the vertical asymptote, we have this point here, and so we're going to get this a very similar behavior, right? It's going to, as it goes to the left, approach the vertical asymptote without crossing or touching, heading down, and as it goes to the right, it's just going to ride along the slant asymptote like this. Right? And it's supposed to be symmetric to the origin, which I don't feel like I did a good job of making that look too symmetric, but it should be. They should kind of be mirror image looking curves of one another. So that is the graph of that particular function. Sorry I went a little bit over on time on the video. Anyways, when we reconvene for class, if you have any questions about this topic, please let me know. Keep up the good work, and I will see you for section 3.6 next time.